Hello, students. Jumping into section 4.2. Now, this one talks about the idea of prime and composite numbers and really demonstrates, again, this is kind of a grade 4 topic from the Common Core. Find all factor pairs. Recognize a whole number is a multiple of its factors. Determine whether a whole number in the range 1 to 100 is prime or composite. And I think what happens is a lot of times we have maybe some kind of memory of what it took to be a prime or what it took to be a composite or how to check, or maybe even something that a teacher might have told us that may or may not be completely true. I remember sometimes teachers would tell me something and it worked for a limited situation, but not in general. Well, let's take a look then at the big idea here. So if you took a number, in this case, the example in the book was 12. They took the number 12 and they tried to write it out into however many different rectangles they could make. Now, this uses the area model of multiplication. So anyway, that's kind of the idea. So when they're looking here, they would say, okay, well, I know I can make this rectangle, which demonstrates that 1 times 12 is 12. And you can see no matter what you have, no matter what number, you'd always have a 1 times that number as an option. And then here we'd have, I could do a 2 times 6. I could do a 3 times 4. But if I tried to make a 5 times something, it wouldn't actually make a rectangle. I wouldn't have enough to finish that off. So in this case, what we could say is there's 1, 2, 3, 4, 5, 6 different divisors is what we call that. 6 numbers that would evenly divide the number 12. Okay, for the number 7, yeah, not so great, right? Because there's only 1 times 7. You could try using 2, but again, it won't make a rectangle. You'd be off by 1 square. Okay. So it does hit the definition down here at the bottom of the page, and to make sure we're all in the same place when we say it here, any whole number with exactly 2 distinct whole number divisors is a prime number. So it does require you to have 2 distinct whole number divisors. Okay, so now I'm going to turn the page, and then we're going to do just a little bit of this. If you're looking at this page together with me, let's jump in. Let me get a little white space here, and we'll do some of this work ourselves. Okay, so here we go. There we are. All right, so this is a table that talks about the number of divisors. And so let me change this back to red, let's say. So the number of whole number divisors. So if my number had 2 divisors, I would put it in this column with the 2. And so what we're going to do is we're just kind of roll through a few numbers to kind of get the idea for it. So the number 1, for example, if I was writing it out box-wise, it would simply be a single box because the only way to write 1 is with 1 times 1. So when it says the number of divisors, even though it's 1 times 1, that does not have 2 distinct divisors. There's only 1 divisor there. Okay, so the number 1 is kind of in column number 1. Let's see here the number 2. Well, the number 2 I could draw as a rectangle like this, which would be 1 by 2. So that one would have 2 divisors. I put it in the 2 column. The number 3, let's see here the number 3, I could definitely write in rectangular form as a 1 by 3. I can't make another one. So that's it. So the number 3 actually goes in the column for 2 because the number 3 has 2 divisors. Okay. Let's go to the number 4. Okay, so the number 4, don't forget, we could always make kind of that long string. There we go. That's a 1 by 4. Oh, but I could also make a little grid that looks like this, which is 2 by 2. That uses 4 squares. So let's see here. We have 2 by 2 and a 1 and a 4. So the numbers would be a 1, a 2, and a 4. That's 3 divisors. So I put the number 4 in column 3. Okay. The number 5 is only the 1 times 5. So I put that right over here. Let's see here. The number 6. 6 would be a 1 by 6 or, oh, there we go, a 2 by 3. So 2, 3, 1, and 6, there would be 4 divisors. So in the 4 divisor column, the first one I would get is the number 6. The number 7 has exactly 2. The number 8, turns out if you kind of draw it out, you could have a 1 times 8 or a 2 times 4, which gives you 4 divisors. The number 9 9 has 1 times 9, but also 3 by 3. So that would be a total of 3 divisors. And then the number 10. So a 1 and 10, 2 and 5, that's 4. So it looks like we're making some patterns here, right? A 6, an 8, a 10. So maybe we're kind of looking here. It looks like 12 is going to be right down this column too. Let's see here. Number 11 has exactly 2. And number 12, let's see here. 12 would be what? A 1 times 12, a 2 times 6. Oh, and a 3 times 4. That's the one we did on the other page. There's 6 of them. Oh, wow. That's way over here. Okay. All right. That's fine. So here's 12. 13. We go back over here because it's just a 1 times 13. 14 would be a 1 and a 14 and a 2 and a 7. So that would come in here, 14. 15, 1 and 15, 3 and 5. So 15 would actually go in the same column for 4. And let's see here, then 16. Well, let's see here. 16 would be 1 times 16, 2 times 8, and 4 times 4. Okay, 4 times 4. So 1, 2, 3, 4, 5 factors. Okay, so 16 would be here. Interesting. Okay, so 16, 17 back over here. 18, well, 18's weird, right? 1 times 18, 2 times 9, 3 times 6. Okay, 1, 2, 3, 4. So 6 of them. So that actually goes in column 6. Number 19 is back over here. Number 20, right? 1 times 20, 2 times 10, 4 times 5. Okay, so 6. Got it. So 6 goes over there. 21, 1 times 21 and 3 times 7. So that would go back over here. Interesting. So I'm starting to see a couple patterns here, and I hope you are as well. There's nothing else that's going to be in this first one. So 1 is truly the loneliest number that you'll ever do. Let's see here. 3, so so 2, a 3, a 5, a 7, 11, 30. So numbers with exactly 2. So those look like my prime numbers. And what's interesting is right next to it, I have 4. Right next to 3, I have 9. Let's see here, right next to 5. Let's see here, 5 times 5 would be 25. 25 would have a 1 of 25 and a 5 and a 5. So actually 25 would go here. Oh, oh, interesting. So yes, these numbers right here look like a prime number squared. Okay, that's interesting. So prime numbers would be here, like prime number to the first power. And then, so the next column over sounds like it would be primes to the third power. Maybe we can make kind of a pattern there. So prime to the third power, let's see here, 2 to the third power, 2 times 2 times 2 would be 8. Yeah, 8 does show up here. Let's see here, 3 times 3 times 3 would be 27. Well, that would be 1 and 27, 3 times 9. So yeah, 27 actually would be in here. So yeah, p cubes are definitely in here. So cubed primes are in here. That's kind of cool. But 6 is not a cubed prime. Um, hmm. Oh, but 6 is 2 times 3, which is 2 prime numbers multiplied together. Okay, interesting. Okay, so just one of those, but they're multiplied together. Let's see the number 16 here. Well, that's 2 times 2 times 2 times 2, so 2 to the fourth. So this would be like prime to the fourth power. Okay. Let's see here. And then over here, yeah, we'd have prime to the fifth, prime to the sixth, prime to the seventh. So those look like prime numbers. We're kind of making a pattern there. But 6, let's see here. 6, 12. The number 12 is 4 times 3, which is 2 squared times 3. So 2 squared times 3. 18 is 2 times 3 squared. 20 is 2 squared times 5. Kind of looks like prime numbers, but one of them squared, one of them isn't. Interesting. Okay. So what we actually have in this table then is the number 1 is extremely special. The number 1 is not prime. If it was prime, it would be in the column with all the primes. It's not. So 1 is not prime. It's also not composite. Because in order to be composite, you have to be able to be factored into primes. So yeah. So if you have exactly 2 factors, you're prime. Anything else in the table, we're going to call composite. So we have composite, which is if you have 3 or more divisors, whole number divisors. If you have exactly 2, we're going to call those primes. And then over here, 1, we're just going to call that's just special. Yeah, it's not prime, it's not composite. Okay. All right, let's move on from there and see how we did. Woohoo! We did all right. Matched all of those. And let's go ahead and keep moving on. So when it says show things that are composite, if you can find something that divides it, it is composite. So like 2 divides it, that works. For 1001, we could use the test for 11. That looks fine. 2781. So if I add those digits, they add up to 9 plus 9 is 18. So 3 divides this. And it says show that these are composite. Oh, yeah. So 3 times 5 times 7 times 11 times 13. That's a bunch of odd numbers multiplied. What we saw previously is that the set of odd numbers is closed. So an odd number times an odd number is still an odd number. And yeah, so if you looked at this, then what you have here is an odd number. And then guess what do we do to it? We add 1. And you take an odd number and you add 1, it has to be even. And if it's even, it's divisible by 2. So yeah, I don't know 2 times what, but that doesn't matter. It just says show that they are composite. It doesn't say to find what the factors are. So I know 2 goes into that evenly. So then we have something called prime factorization, which is the idea that we can write a number uniquely in its prime factorization. Take a number like 260, break it down into factors, continue breaking down into factors until the only thing you have left are prime numbers. That is kind of like a number's social security card, right? It's unique. Every one of you has your own social security card. Nobody else is going to have the same number. So this is a unique way of writing a number. So how can you do this? There's a lot of ways. There's a visual way. This is known as a factor tree. It is not the only way. And we'll actually show a few different ways that we can find the prime factorization, I guess I should say. So a factor tree is fine. Just start with your number and break it down into 2 factors, then break those down into factors. If you hit a prime number, stop. So that's the only piece I would kind of say. So right here, when you hit the number 2, just stop. That branch dies. Continue with the rest of it. 130 is 2 times 65. Okay, 2 is prime. So stop that branch. Continue working your way down. But I think what's cool about factor trees is no matter if you do it different than someone else, this person got a 2, then a 5, then a 13. Over here, they got a 2, then a 13, then a 2, then a 5. You are going to get the exact same answer for prime factorization that anyone else will. And that's because of something called the fundamental theorem of arithmetic. And it says every composite number can be written as a product of primes in one and only one way. With the exception, again, multiplication is commutative. So if you start with the smallest primes and work your way up, then there will be exactly one way to do it. If you think about kind of trying to be like, oh, but I could change the order, it's still multiplication, right? So as long as you think about that, then it will be unique. Okay. So a couple other ways that you can go through and do it. One is the alternative form. This is not a factor tree. For some people, they find this to be a little bit quicker. Simply divide by a number that works and go from there. So usually when you're doing this technique, you would start with primes. So start with the prime of 2. If it works, great, use it. So they used it. They divided 2 into 260. They got 130 left. Divided 2 in again. They got 65 left. They notice it ends in a 5, so they divide by 5. And the last piece is left is a 13. Yeah, I think that's probably, I don't know how many more of those that you would want someone to do. Again, this is how you would check it. Find a prime that goes in, divide it, make the number smaller. Repeat the process until you get down to the number 1 at the end, because then you're out of all of your primes. So this is a textbook page about a school book page, finding prime factorization. Okay, so prime factorization is listed as a grade 6. However, prime numbers are often listed earlier than that, as we saw, grade 4. And in elementary school classrooms, oftentimes what you'll do to find not just primes, but also composites as ways to break up composite numbers is to use something called a Cuisenaire rod. Cuisenaire rods are different length. They're all in centimeter length. So you have from 1 centimeter long down to 10 centimeters long, and they're different colors. Different colors because everything that is a yellow would be 5 centimeters long. Everything that's dark green would be 6, and so on. So what you can do is you can kind of say, hey, look, here's a set of numbers, 3 of whatever piece I have, in this case, purple. 3 purples gives me 12. Well, that's the same as 4 greens. So we can see, oh, that's a different way of factoring it. And lastly, that's the same as 6 reds. So 6 red, 4 greens, and 3 purples. So if we kept going, you could add another one. There's a dark green here that is 6. You could use a 6 and a 6. That would also get you there. So when we look at numbers and we try to factor them, if you can find a number that factors, you actually typically you pick up another number for free. So you remember when we did 12, right? 12, and you say, well, what goes into 12? Well, you can see a 2 goes into 12. The other number, now you may already know it because you're kind of familiar with multiplication. But for a student, if they're unsure of it, that other number is what you get when you do 12 divided by 2. That's the idea of the missing factor approach to multiplication and division. So 12 divided by 2 becomes your other number. So that's how you can find. If you can find one factor, do division, you can find the other factor. Okay. And that's what theorem of 4-13 says. It says if you have a number that is a divisor and you're not dividing into 0, that's a key piece, then the number divided by d is also a divisor of n. Okay. So yeah, like if you had your calculator to try to find kind of what a factor was, I think we said, I did a division video, 5, was it 828, something like that? And I said, okay, well, 17 does divide into this number. So in order to figure out how many times it divides in, we could rewrite this as 55828 is equal to 17 times some number. That number is what I get when I do 55,828 divide by 17. So if I do that, 55,828 divide by 17, and I get 3,284. So basically this number right here is 55,828 divided by 17. And that's how I get 3284. So that's how I can find another factor pretty quickly. If you know one factor, you know another factor. Um, well, almost, right? With one little tiny exception. And the idea is think about the number 36. Well, somebody could say, well, 6 goes in evenly. You're like, aha, yes, it does. Then 36 divided by 6 would be my other number, but 36 divided by 6 actually turns out to be 6 itself. So I guess what I'm saying is sometimes if a number divides, it doesn't mean that it won't match. It doesn't mean it have to be unique. It's okay. Sometimes you're going to find things that work out perfectly, which is another way of saying, hey, we got to be careful when we get to these things that look like perfect squares. Okay, you're not going to get 2 factors out of a perfect square every time. You're going to get it sometimes, but not all the time. So if you were trying to look at how many divisors a whole number had, remember that table we had um, a couple pages ago, the idea could be to say, well, wait a minute. I know what divides, let's say, particular numbers. And in this case, they're doing the number 24. How many total divisors does it have? So what they do is they say, well, wait a minute, let's look at each of the prime numbers that we have. And 24 is equal to 2 cubed, which is 8, times 3. So this is the prime factorization. Now in the prime factorization, you have the number 2 by itself. and you think, what divides the number 2 guaranteed? And the number 2 would be divisible by 1, 2, 4, and 8. Okay, so it has 4 factors, 4 divisors. If you need to, you can actually relate that back to the exponent here, because the number 1 is 2 to the 0, 2 to the 1 is 2, 2 squared is 4, and 2 cubed is 8. So what we're really looking at is kind of saying, okay, count up and start at 0 and say from 0 all the way up to 3, those all work fine for us. Now the number 3, you could rewrite 3 as 3 to the 1, and you'd say, well, that has just a 1 and a 3. So if you're counting, there would be 2 factors here. Why is this important? 2 cubed has 4 factors. 3 to the first power has 2 factors. And if you went up here and looked in the chart, you'd actually see there's 1, 2, 3, 4, 5, 6, 7, 8 factors total. Not a coincidence. So for every one of the kind of the ones that I've done in blue here that involve a 2, for every one of those, you could select one of the factors in green to make a new number. And this is the fundamental counting principle. Like if I had this many shirts and this many pants, how many outfits could I make? It's the same idea. And so we end up with 8 total divisors. Okay, 8 total divisors. That's kind of a cool way to do it, though. When you look at it, it was really just, hey, if I can prime factor it, I can tell how many divisors it has, and I don't need to go that far. And that's what this theorem describes to us. It says, hey, break it down into primes. And then because we have to count the 0 part, you add 1 to each of those exponents, and then you multiply those to find how many whole number divisors you have. Okay. So if you had the number million, right? The million has a lot of factors. But if we break it down into its primes, it's really a bunch of 2s and 5s because they all make 10s. So break it down, you have 6 2s and 6 5s. Then what you would do is say, well, wait a minute. For 6 2s and 6 5s, 2 to the 6th and 5 to the 6th, the number of factors would be 7 times 7, which would be 49. And that's how you can figure out how many total factors there are. Okay. Notice this doesn't tell you all the factors. If you go back to that table and you think about kind of writing all of the options down for like 2 to the 6, that would be 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, all the way up to 2 to the 6. And then 5, you do the same thing. 5 to the 0, 5 to the 1, 5 to the 2. You do that, and then you do the Cartesian product. So you take one of the first one with this, one of the first with the next, one of the first with the next, and that's how you can make every possible factor if you needed to. All right, so now how to tell when a number is prime or not. There's a lot of ways we can do that. One, we can say, hey, it has to have exactly 2 factors, which is great if you can see that it has exactly 2 factors. Yeah. So one of the things we're going to do in class, we'll do an activity link to this in class that will help us see. But what you get to know is if it is composite, there has to be that pair of factors, one below and one above. And so for the number 32, you could have a 2 times 16. Okay. For the number 32, you could also have a 4 times 8. Okay. For the number 36, we could get a 4 times 9, but we could also get a 6 times 6. So I think what happens is when we hit that dead center right on, when it's the same number twice, which means the number is a perfect square, that's where we're kind of like, okay, if it's a perfect square, then I don't have that pair of numbers, because like for 36, I have 6 times 6, and those aren't unique. All right. So what we have is these beautiful squares, and this again is kind of like the Price is Right. So when you look at these perfect squares, you get to see why we end up looking like, if I'm looking for a number in like the 101, is 101 prime? Well, we actually can square all of our prime numbers out and say, wait a minute, 101 is between 7 squared and 11 squared. So I need to check to see if I have factor pairs with the prime numbers up to that value. And that's what theorem 415 says. If n is composite, it must have a prime factor p such that p squared is less than or equal to n. It's got to be less than almost all the time, unless n turns out to be a perfect square, in which case it would be equal to. So if we were checking a number like 91, let's just say I wanted to check 91. Let me throw some white space in here. And if we were going to check number 91, is 91 composite or prime? Many of you might say, hey, I know it's composite because it's not divisible by 3 and it's not 5 and it's not 2, or I can check a few primes and it just doesn't seem to work out. Well, we need a little bit more than that to guarantee that it is or is not. So is 397 prime, is 91, we'll do 91. Is 91 prime or composite? Well, if I was writing my list of prime squareds out, let's see here, 5 squared equals 25, 7 squared equals 49, 11 squared equals 121, and I would say, okay, 91 is sitting right here between these two. Okay, somewhere up in here. So I don't need to go as high as 11, but I do need to check 2, 3, 5, and 7. So what we can do very quickly is we can check 2. We can see 2 does not divide the last digit. So 2 does not divide 91. So 2 is out. We could check 3. To do that, we add the digits together. 3 does not divide 10, which is the sum. So therefore, 3 does not divide 91. Okay, so 3 is out. 5, same thing, last digit, right? 5 does not divide 1. Therefore, 5 does not divide 91. Okay. So I've just checked 2, 3, and 5 using divisibility tests. And the last one is 7. And 7, this number I can't tell with 7. So I'm tempted. I could just do long division. I could do short division, long division. I could also just break the number up into something I know is divisible by 7. And if I rewrite this as 70, because 7 goes into 70 pretty quick and easy, then I'm left with 21 afterwards. And I would say, oh, yeah, if it works for 70 and it works for 21, then 91 is divisible by 7. Okay, you want to know what it is? 91 divided by 7 will tell you. Or you could break this down into sevens and say this is 10 groups of 7. This is 3 groups of 7, which would tell you it's 13. And that's how we would know this is equal to 13 times 7. So definitely composite in that case. Very cool. There's a talk here about a sieve of Eratosthenes. We're actually going to do something like this in class. This sieve of Eratosthenes is actually given in grade 1, where they're kind of coloring things and checking things. So we'll talk about that as we go. Yeah, so this is problem solving about perfect squares. This is a really interesting one. It says, if you have a whole number that is a perfect square, then it has to have an odd number of divisors. And that kind of goes if and only if. So if it has an odd number of divisors, then it has to be a perfect square. And you could actually go back to our table and see that. The odd divisors would be the 3, the 5, the 7. And when you look at 3s, yeah, they were all perfect squares. All right. Lastly, there's a case about kind of talking about, well, how many primes are there? How many primes are there? Maybe there's a fixed number. Maybe we could write them all down. Maybe not. So if we assume, so this is an interesting idea, but I like it. It goes along with our justification portions from previous chapters. So if we assume that that the number is finite, so assume there are finitely many. Okay, finitely many primes. I don't know. I don't know how big that is, but we'll just call this to be the biggest prime number. So let's say this is the biggest prime number, right? Then what I could do is I could actually multiply all the primes together. So 2 times 3 times 5 times 7 times 11 times ... and just say multiply all of those together. And then when I get to the end, multiply by m, because m is the biggest. Okay. That creates a massive number. It's going to be very large. Okay. Now take that number and just add 1 to it. Well, then this new number is not divisible by any number on the left-hand side. It's not divisible by 2 because, right, this thing over here is an even number, and then I add 1 to it. So it's not going to be divisible by 2. And so if you look at it here, what you could say is that 2 divides this number, but 2 does not divide 1, because that's my other number over here. So therefore, 2 does not divide big, crazy looking thing plus 1. And you could do that for every prime number all the way up to m. You could say, hey, this one doesn't divide anymore because my prime number of 3 does not go into 1, or my prime number of 5 does not go into 1. So what happens is basically you created a new number by taking all those primes, multiplying them, and then adding 1. And it's a great idea. What it means, though, is you have a new prime number, because a prime number would have to be, two prime number. A composite number would be the product of 2, and we wouldn't have that. So if we assume there are finitely many primes, and if we assume from that we found the biggest one, well, right afterwards, we just found a new prime number that has to be bigger than that one. So this would be a fail. So if you go online later, you watch a video where somebody says, oh, there's finitely many primes, I'll show you. You would actually be able to say, yeah, go ahead, tell me what's the biggest one. And then we could actually say, sorry, it can't be, and here's why. Okay. Yeah, so there's a nice problem-solving problem here about selling stuffed animals, or bears in this case. I think the biggest thing to take away from this is if you have two numbers, and we'll actually see more of this in the next section, but if you have two numbers and they are both multiples of some number, like we're selling bears for a certain price, maybe it's like Build-A-Bear Workshop, and hey, here's the price of a bear. And that's great. One day we sold this many, one day we sold another number, and somebody forgets to write down how many, but they just write down how much money was brought in. Then what you could say is, okay, I actually know then that whatever it is, I would need to multiply the price of the bear times the number of bears. So maybe I'll do it that way. Price of the bears times the number of the bears. And then you look here and you're like, well, the price of the bears didn't change, but I definitely had more sales on that one. So more sales looks like this. But you could also say, well, wait a minute, right? That's to get to the higher number. I could have just started. I must have sold at least $1,843 worth, and then I sold some more. And if you do that, what you could see at the end is, oh, that's interesting. The amount more that you have would be here. So P would be a divisor. Whatever this P value is, it would divide your 1843, it would divide your 1957, and it would divide the sum or difference of these, which is pretty cool. And the reason why I say that is I don't want to try to factor 1,957. I don't want to do that. I don't want to try to factor 1843, but if I subtract here, I will get a number that has to be divisible by whatever numbers they both divided. It's the number of, well, I guess it's the price of the bear. And so this right here would be the price times some number. What it means, if you're trying to figure out how many bears I sold on each day and how much I sold them for, if you can think like this, you get to a much smaller number that's easier to work with. Like this would be 2 times, 57 to get to 114, which now I'm having to prime factor 57. But 57 is what? 5 times 7 is 12. So 3 goes in. 3 goes in, and 3 times, 19? 3 times 19? Yeah. So now what I can tell you is it says the price of each bear is a whole number and it's greater than $1. So either they sold the bears for $2, $3, $19, or if you wanted to go all the way to the other end, $1. Okay, so there we are. Has to be factors of this. I guess technically it could also be a $6 bear because it has to be one of the factors. A $38 bear or a $57 bear. So we have a lot of options here as to what they are, but it has to be here. These prime numbers would have to divide how much there is. So that's why prime numbers are here. Prime numbers are often called the building blocks of a number. Oh, and that's it for 4-2. So it's a building block of a number. And when you think of it that way, you realize how fundamental the prime numbers are to multiplication of numbers. We don't have that same power when it comes to addition. Right? With multiplication, you really limit the options, and that's not the case with addition. Because with addition, I raise one by 3, I lower the other by 3, I get the same result. And while you can do that with multiplication here with a prime number, there's no kind of unique way of writing it because we could have a lot of different ways to add things together. Okay, that wraps up 4-2. Gonna go ahead and take a little bit of a pause, give you a chance to catch up on this, start some of the homework. We'll have a couple activities related to this, so bring your activity manual if you're watching this before class, and I'll see you soon. All right, off you go.